When you build your first few models, it can feel satisfying to split the data once, train once, and report a score. But that single split can be more like a coin flip than a reliable measurement. Some splits are easy because the test data looks a lot like the training data, and some splits are hard because the test data contains rarer cases or a different mix of behaviors. Cross-validation exists to reduce that luck factor by evaluating a model across multiple train and test partitions, giving you a fuller picture of how performance holds up. The goal is not to make the number look higher, but to make the number mean something. For brand new learners, the key is understanding that cross-validation is as much about honesty as it is about statistics, because the wrong cross-validation setup can accidentally leak information and produce impressive results that vanish in real use. If you learn the correct habits now, you will avoid one of the most common reasons model performance disappoints after deployment. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The basic idea of cross-validation is to reuse your dataset efficiently by taking turns holding out different portions as the test set while training on the rest. K-fold cross-validation is the most common pattern, and it works by splitting the data into K roughly equal parts called folds. You train on K-1 folds and evaluate on the remaining fold. Then repeat until each fold has served as the test fold exactly once. At the end, you average the scores to get a more stable estimate than a single split can provide. This helps because each data point gets a chance to be part of the test evaluation, and the model is tested across a variety of train test boundaries. A beginner-friendly way to think about it is that you are running several mini-experiments instead of one, and you are looking for consistency rather than one lucky win. That consistency becomes a form of trust, because it suggests the model is not relying on a particular accident in one split. Folds need to be constructed thoughtfully, because the way you partition the data determines what the evaluation actually tests. If you split randomly, you are assuming that any row is exchangeable with any other row, meaning the data points are independent and identically distributed. That assumption is sometimes reasonable for carefully collected datasets, but many real datasets are not like that, especially in operational environments where rows are connected by user, device, customer, or time. When rows are related, random folds can accidentally put nearly identical examples in both training and test folds. That makes the test easier than real deployment, because the model is effectively seeing the same patterns in training and then being asked to predict a near duplicate in testing. This can create scores that look strong while hiding the fact that the model is mainly learning identity or repetition. Correct cross-validation begins with respecting the structure of the data, not just slicing it evenly. Leakage avoidance is the most critical requirement for cross-validation, because leakage can sneak in even when you think you are evaluating correctly. Leakage happens when information from the test fold influences training, directly or indirectly, so the model has an unfair advantage. Sometimes leakage is obvious, like including a feature that contains post-outcome information, but cross-validation introduces more subtle leakage paths. For example, if you compute normalization parameters using the full dataset before creating folds, you have allowed test fold values to influence the transformation applied to training. If you perform feature selection using the full dataset, you have allowed the test fold to influence which features are chosen. Even if you never touch the labels, you can leak distribution information that makes the evaluation unrealistically optimistic. The right discipline is to treat each fold like a miniature deployment simulation, where everything that learns from data must learn only from the training portion of that fold. When you build that habit, your scores become meaningful rather than flattering. This is why people often talk about pipelines as the safest way to do cross-validation, because a pipeline ensures that all pre-processing steps are fitted on training data and then applied to the held-out fold without refitting. In a well-disciplined setup, scaling, encoding, dimensionality reduction, and feature selection are not performed once on the entire dataset, but performed separately inside each fold using only the training split of that fold. That can feel repetitive, but it is the price of honesty. Beginners sometimes resist this because it seems slower, Yet the alternative is producing a score that is partly an artifact of data reuse. In security and cloud contexts, where you might be building a model to detect abnormal authentication behavior or risky configuration patterns, the difference between an honest score and a leaked score can be the difference between a useful system and a false sense of safety. Treating preprocessing as part of the model and folding it into cross-validation correctly is one of the most important quality habits you can build. Another part of using folds correctly is choosing K in a way that matches the size and variability of your dataset. If K is very small, each test fold is large, but you have fewer evaluations, so your estimate can still be noisy. If K is very large, each test fold is small, and the training sets are large, but the evaluation on each fold can become unstable because the test fold contains too few examples, especially for rare classes. A classic extreme is leave one out cross-validation, where each test fold contains one example, and while it uses data efficiently, it can have high variance in the score and can be expensive. The practical goal is not to memorize a perfect K, but to choose a fold scheme that provides enough repeated measurements without turning each measurement into an unreliable tiny sample. In imbalanced or rare event settings, you also need to ensure that each fold has enough positive cases to evaluate meaningfully. Cross-validation is supposed to reduce luck, so you do not want a fold design that reintroduces luck by making folds too thin. Stratification is a technique used to make folds more comparable when you have class imbalance, because it tries to preserve the class proportions in each fold. For example, if only a small fraction of your data points represent attacks or failures, a purely random split could create folds with almost no positive examples, making evaluation noisy and misleading. Stratified folds make it more likely that each fold includes a representative mix of classes, which stabilizes metrics and reduces the chance that one fold produces a wildly different score simply due to missing rare cases. The beginner lesson is that cross-validation is not only about repeating splits, it is about making those splits fair and informative. However, stratification does not solve every problem, especially when data points are correlated by identity or time. You can preserve class proportions and still have leakage if the same entity appears in both training and test folds. So stratification is helpful, but it must be paired with structure-aware splitting. Group-aware splitting matters when multiple rows belong to the same entity, such as the same user, device, account, or organization. In those cases, the safest approach is often to keep all rows from a given entity in the same fold, so the model is tested on entities it did not train on. This prevents the model from learning entity fingerprints and then appearing to generalize when it is actually recognizing the same entity. In cloud telemetry, entity linkage is common because a single user can generate many authentication events, a single service can generate many metrics, and a single host can generate many log lines. If you split randomly at the row level, your evaluation can become a proxy for how well the model recognizes known entities, not how well it predicts new behavior. Group-aware folds test a harder and more realistic question, which is whether the model can transfer its learning across entities. That is often the question you truly care about in security analytics, because new devices and new accounts appear constantly. Time-aware splits are the next level of discipline, and they are essential whenever data has a meaningful time order and the model will be used to predict future events. If you shuffle time, you create a training set that contains information from the future relative to the test set, which is not how deployment works. Even if you do not leak labels, you leak context, because the future distribution can shape what patterns the model learns and what transformations are fitted. Time-aware evaluation respects the arrow of time by training on earlier periods and testing on later periods. This makes the evaluation more challenging, but it also makes it honest, because it simulates how a model will face new data after it is trained. In many real systems, the biggest threat to generalization is that the world changes, so time-aware splitting is the only way to see whether your model survives that change. When learners ignore time order, they often report excellent scores that collapse when the model faces the next month of data. Time-aware cross-validation often uses rolling or expanding windows, where each fold trains on a historical window and tests on the immediately following window. The important conceptual point is that each test fold comes later than the training fold, and you do not allow information to travel backward. This approach reveals how performance changes as time moves forward, and it can expose concept drift, which is when the relationship between features and outcomes changes. In cloud security, drift can happen when new authentication methods are introduced, when logging schemas change, when user populations shift, or when attackers adopt new techniques. A rolling evaluation can show that the model performs well for a while and then degrades, which is valuable information because it tells you that you may need retraining schedules or features that are more stable. Beginners sometimes assume cross-validation always means random folds, but time-aware cross-validation is the correct version for time-driven problems. The technique is the same idea of repeated evaluation, but the fold design respects reality. Leakage avoidance becomes even more important in time-aware setups because temporal data makes it easy to accidentally bake future knowledge into features. Any feature computed using an entire time span must be carefully defined so it uses only information available up to the prediction point. For example, a customer's average activity over a month cannot be used to predict an event that occurs midway through that month unless the average is computed only from the days before the event. Similarly, if you compute global statistics, like encoding categories based on target rates, you must ensure those statistics are computed only from the training window for each fold. These details can feel tedious, but they are exactly where real-world failures originate. A model that sees future aggregates can look extremely accurate and then fail abruptly because those aggregates are not available in production at decision time. The discipline is to imagine a strict timeline, then verify that every transformation and aggregation respects it. If you cannot defend the feature as something known at the time of prediction, it does not belong in the training input. Another beginner trap is using cross-validation results as if they guarantee performance, without noticing that the folds might still not reflect how the model will be used. If your deployment will face new regions, new customer segments, or new systems, but your folds always include those groups in training, your evaluation may underestimate risk. This is where you should think about what kind of generalization you need, because there are different kinds. Sometimes you need to generalize across time, sometimes across entities, and sometimes across both at once. A cross-validation scheme that is good for one kind of generalization might be weak for another. For example, group-aware splitting tests generalization to unseen entities, while time-aware splitting tests generalization to the future, and combining them can be challenging but important in dynamic environments. The deeper point is that cross-validation is not a ritual you perform. It is a design choice that should match the future you are trying to predict. When your fold design aligns with deployment reality, the average score becomes a meaningful summary of risk. Cross-validation also interacts with hyperparameter tuning, and this is where many learners accidentally overfit the evaluation process. If you use the same cross-validation folds to choose hyperparameters and to report final performance, you can still get an optimistic estimate because you are selecting the best settings based on those folds. A more disciplined approach separates the tuning process from the final evaluation, so the final score is measured on data that was not used to make any choices. Even without getting lost in terminology, you can understand the principle. If you look at a set of results and pick the best one, you are benefiting from luck, so you need a fresh test to confirm the win is real. In practice, this often means you keep a final holdout test set that you do not touch until the end, and you use cross-validation inside the training set to tune. For beginners, the key lesson is that evaluation is easiest to corrupt accidentally, especially when you are eager to improve scores. Cross-validation helps reduce variance, but it does not remove the need for careful separation of decision-making and measurement. By the end of this topic, you should be able to treat cross-validation as a disciplined way to measure generalization rather than as a button you press for a better score. Folds are not just chunks of data. They are miniature simulations of how your model will encounter the world, so their construction must respect identity, correlation, and time. Leakage avoidance is the non-negotiable rule that every transformation, encoding, and selection step must be learned only from training data within each fold. Otherwise, your evaluation becomes a flattering illusion. Time-aware splits are essential when predictions are made into the future because random shuffles hide drift and allow future context to leak into training. When you combine these ideas, Cross-validation becomes a tool for earning trust because it reveals whether performance is stable across different partitions and realistic conditions. If you build the habit of aligning fold design with deployment reality, your model development stops being a search for high numbers and becomes a process of producing results that hold up when the data changes.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.